Okay, so we've been talking about conduction problems that were one-dimensional and steady state, and the problems that we've dealt with so far were truly one-dimensional, right? They weren't approximately one-dimensional, they were actually one-dimensional. So for example, we had conduction through a cylinder or a cylindrical shell, and we had made the boundary conditions such that energy only wanted to go in one direction, and therefore there would only be temperature gradients in that direction. There was no energy movement in any other direction, right? And so it was a purely one-dimensional problem. Today we're going to start talking about a class of problems that we're going to model as being one-dimensional, but they really aren't. Right? We're going to approximate them as being one-dimensional, and those are called extended surface problems. So just to try to illustrate what I'm talking about, I've tried to draw here a fin. So this is an extended surface, or a piece of metal typically that you would attach to a wall. So here's my wall, and it's at some temperature T sub B, and the wall is exposed to convection, so heat transfer coefficient and T infinity. And one way that I can improve the rate of heat transfer from the wall to the gas is by putting these what we call fins on the wall. So we'll attach a piece of metal, in this case it's a rectangular piece of metal, to the wall, and what that does is if the metal is conductive enough, it gives the convection process a lot more surface area, because now instead of just having this amount of surface area to convect from, it has both sides of this and maybe even the tip to do convection from. So that's a fin. If you think about this problem, this is a problem that is absolutely not a one-dimensional problem, right? If I imagine what energy has to do, so let's see here. If I am a piece of energy and I start my travel right here and I want to get out, what do I have to do? Well, I have to move by conduction both in the x direction but also in the y direction, right? And that gets me to the surface, and then once I'm at the surface, then convection takes me to the surroundings. So this is not like problems we've talked about before, where conduction was only happening in one direction and therefore temperature gradients are only in that direction. Here we have conduction happening in both the x and the y direction, and therefore it's unavoidable that we will have temperature gradients in both the x and the y direction. This is a two-dimensional problem, right? Temperature in this fin is going to be both a function of x and of y. So we can look at that temperature distribution. I'm not sure what's going on here. Sure, let's keep. So let's look at the temperature distribution. If I can make technology work for me. So here's my fin again, and we said that energy had to move both in the x and the y direction. So the temperature distribution in that fin might look something like this. So let me explain what I'm showing here. This is temperature as a function of y, and each of these lines is a different value of x, right? So this is temperature plotted from y equals 0, so y equals 0 is the center line, out to y equals th over 2, so the edge over here, right? And what I'm doing here is I'm just showing you that temperature at various values of x. Excuse me. So this is at x equals 0. This is the temperature right along this line. It's all at the base temperature. That makes sense. This is at x over L equal 0.25. So here I'm a quarter of the way down the fin. So here we have x over L equal 0.5. That's this line here, and that would be right along here. 0.75, 3/4 of the way, so that's along this line here. And finally, x over L equals 1 is right along the tip here. And I guess one thing to point out here is that, clearly temperature is both a function of x and y, right? So temperature is changing as I move in the x direction, right? As I move from x equals 0 to x equal L, temperature is clearly changing. But temperature is also changing as I move in the y direction, right? So as I move from the center to the edge, the temperature is changing. So it's a two-dimensional problem, as it should be. And because it's a two-dimensional problem, we can't solve this problem using thermal resistances, right? That's all of our thermal resistance equations came from these one-dimensional solutions, but that doesn't mean that we can't use those thermal resistances to understand the problem, right? Because that's, as I've said several times, kind of our main tool for doing that. And the way you think about a problem like this is you have to realize that each of the heat transfer mechanisms comes with its own thermal resistance, right? There's a different level of difficulty associated with moving energy by heat transfer, by conduction in the X direction, so there's a thermal resistance associated with that, by conduction in the Y direction, so there's another one associated with that, and then by convection from the surface to the surroundings, so yet another one associated with that. So these are approximate concepts, right? Clearly, I can't just somehow combine these resistances and get an exact solution, but that doesn't mean that by calculating these resistances and looking at their magnitudes, I can't understand the problem pretty well. So that's what we'll do, is we will estimate each of these resistances, and we'll, just to reinforce, that's just an estimate, right? These are estimated quantities. If I have a conduction resistance, and I have two of them here, I said every time I have to estimate a conduction resistance, it's going to be the distance I have to move the energy, the distance to conduct, divided by K times the area for conduction. So if I'm talking about moving energy in the X direction along the fin, the distance that I have to conduct is at least approximately L, and the area for conduction is the thickness times the width, right? So L over K, and then the thickness times the width. If I'm talking about conduction in the Y direction, well, now I'm moving from the center to the edge, so the distance is at least approximately the thickness over 2. And the area then is, if I'm looking in the Y direction, the area is W times L. So this is my conduction resistance. And then once I finally get to this surface, convection is 1 over H bar times the area, and the area is W times L. So these are the three resistances that together govern what's going to happen inside of here, right? And by looking at the magnitudes of these resistances, I can come up with a pretty good estimate for what the final temperature distribution is going to look like. And I can actually see, if I go back to this plot here, I can see the impact of each one of these resistances, right? So as I move energy through a resistance, that's going to cause a temperature drop in the direction the energy is moving, right? So I should see a temperature drop associated with the conduction resistance in the X direction, and sure enough, I see that as I move from the base along the fin in the X direction, this drop from line to line to line is related to how big this conduction resistance is. I should see a conduction resistance in the Y direction, so as I move from the center to the edge, I should see a temperature drop, and sure enough, at every one of these lines, I see a temperature drop. I called this one here delta T conduction in the Y direction as I move from the center to the edge. How big this delta T is related to how big this resistance is, right? And then finally, I should see a temperature drop from the edge to the surroundings, right? So if I get to the edge here, there's a temperature drop from that edge to T infinity, right? And that's delta T convection. So the sizes of those temperature drops are related to the sizes of these three resistances. So what happens then in the case where the conduction resistance in the Y direction, which is causing this delta T conduction in the Y direction, is much, much smaller than the convection resistance from the surface to the surroundings, right, which is causing this temperature difference here, right? So that ratio of resistances is proportional to these two temperature drops. And what you should, I think, be able to see pretty clearly is that if the conduction resistance in the Y direction becomes very small relative to the convection resistance from the surface, then what's going to happen is this temperature drop that I get as I move from the center to the edge is going to become much, much smaller than the temperature drop from the edge to the surroundings, right? And that's the limit where every one of these lines becomes more and more horizontal, right? I'm getting rid of that temperature drop in the Y direction. These lines become horizontal, And if you think about it, that means the temperature is at least approximately only a function of x. And that's the extended surface approximation. Right? The extended surface approximation is, if you step back and think about it, it's this idea that even though I have a two-dimensional problem, the resistance to conduction in some direction is so small that I don't get much of a temperature gradient in that direction. And so I can neglect temperature gradients in that direction and just assume temperature is only varying in the other direction, right? That's what's happening here. The resistance to conduction in the y direction needs to be really, really small. And if it is, well, then I'm not going to get much of a temperature drop in that direction. And so I can ignore temperature gradients in that direction and assume temperature is only a function of, in this case, the x direction. So that extended surface approximation is justified with what's called a BO number, right? So a BO number is, in this case, the ratio of R conduction in the y direction to R convection, right? It's the ratio of the resistance that we want to check out and see if it's really small. Nothing in life is ever small or large by itself. It's always got to be compared to something else. So in this case, you compare that resistance to the resistance from the surface to the surroundings, and you get a dimensionless number that's called the BO number. And if that BO number is really small relative to 1, then you can make the extended surface approximation. Right? For this particular problem, the BO number is R conduction in the y direction, which we said was this equation here, divided by R convection, which we said is this equation here. So if I just divide these two things, I get the thickness times h bar over k. If this quantity is much less than 1, then I can assume that the temperature is only changing with x and not with y. I can make the extended surface approximation. And it should make a little bit of sense here, right? If I have a fin that's really thin, then there won't be much of a temperature gradient across it, right? If it's got a very high conductivity, same kind of thing. And then if h bar is really small, same kind of thing, then I'm going to get most of my resistance to convection. So that makes life easy if you can, or easier, I guess, if you can make the extended surface approximation. It goes from having us solve some kind of two-dimensional problem that involves partial differential equations to a one-dimensional problem that's just going to involve ODEs again. One thing that you need to understand before we move on is that this BO number that I've written down here is the correct BO number for this problem here, right? But there's all different kinds of problems, and this won't always be the right BO number to calculate. The concept of a BO number that you need to remember is the BO number is the resistance to conduction in some direction that you'd like to neglect temperature gradients, right? So this is basically the resistance to conduction that you'd basically like to just throw away as being not important, right? And you're going to then compare that resistance to the resistance from the surface of the object to the surroundings, right? So that's the BO number, and it doesn't always have to be just like we did here, R conduction in the y direction divided by R convection. So for example, we may have a situation like this where now both convection and radiation are important from the surface, right? I still maybe want to use the extended surface approximation, but the BO number I need to calculate is no longer the same. Right now it's changed because I have from the surface both convection and radiation resistances, right? So if I go back to this idea of a BO number, I need to compare the resistance to conduction that I'd like to neglect in my model. Well, that's still R conduction in the y direction, right? I'd still like to neglect temperature gradients in the y direction. I have to compare that with the resistance from the surface of my object to the surroundings. Well, that's changed a little bit now because the resistance from the surface to the surroundings is the parallel combination of convection and radiation, right? But, once I figured that out, the BO number is just me plugging in these different values into that formula, and I get a slightly different answer here, but it's going to tell me the same thing, right? It's still going to be dimensionless, and it's still going to be the case that if that BO number is much less than 1, then I can make the extended surface approximation. If it's not, then I can't. The other thing that's worth pointing out here is the BO number, when I'm using it like this to justify a model, is not an exact thing, right? If I go back here and think about these, where am I at here? Think about these resistances. None of these resistances were exact, right? So you could argue with me about every one of these resistances. You could say, well, I don't really have to conduct all the energy along the length, right? Some of the energy actually makes its exit halfway through. So maybe this should be L over 2. Or, maybe you could say the same thing about our conduction in the y direction. It doesn't really all have to go from the center to the edge. That's kind of a worst case scenario, right? So maybe this should be the thickness over 4. Right, and the point that I want to make here is that you're kind of missing the point if you start nitpicking at factors of 2. These resistances are only there to help you understand their relative magnitude with respect to one another, right? And if you find a resistance is 100 times smaller than another resistance, well, 2 times very, very small is still very, very small, or very, very small divided by 2 is still very, very small. So it's not going to change your conclusion. And once you've used the BO number to make this justification, right? Once you've used the BO number and made this justification, then you never use the BO number again in your solution, right? The BO number is only used in this context for you to make some kind of modeling assumption. It's not then used within the model itself. In fact, if you think about it, once you've made the extended surface approximation, you've really decided that our conduction in the y direction is 0. It's not important, it goes away. I don't have to think about it anymore, right? So if I've decided the extended surface approximation is a valid approximation, now in my problem, I'm really only left with 2 heat transfer processes that are important, right? I'm left with arc conduction in the x direction and arc convection, right? So these are the 2 things that are happening. I still can't use these resistances to solve the problem, right? But actually, I can still use these resistances to understand the solution. So, I have these 2 resistances. Again, if I think about what's going on now, these 2 resistances that are left are going to tell me the relative magnitude of temperature drop due to conduction in the x direction, and then this is going to tell me the magnitude of temperature drop by convection from the surface to the surroundings, right? If I look at what's happened if I make the extended surface approximation, the center temperature and the edge temperature have collapsed. There's not much of a temperature gradient in the y direction, so these 2 things become sort of the same, right? This is temperature as a function of position x, right? And there's not much difference as I look at different y's because the BO number is small. But I am having a temperature drop as I move along the fin in the x direction, and the size of that temperature drop is related to arc conduction in the x direction. I have a temperature drop due to convection resistance from the surface to the surroundings, and the size of that temperature drop is due to arc convection, right? So I can still use these 2 resistances to think about what's going to happen. In fact, let's think about what would happen in the limit where arc conduction in the x direction is really small. And again, nothing's really small by itself. It must be really small relative to arc convection. If that's the case, then I would expect not a lot of temperature drop due to conduction in the x direction. All of my temperature drop is due to arc convection. So what does that look like? Well, I think what that would look like would be a fin where the base temperature more or less persists all the way along the fin, right? There's not much of a temperature drop as I move along the fin. So if I look at that situation, it's basically this upper line here, right? I have the base temperature at x equals 0, and I basically have the base temperature all the way to the tip at x equal L, right? That's the case where arc conduction in the x direction is really small relative to arc convection. In the opposite situation, I could have a fin where arc conduction in the x direction is really big relative to arc convection. And if you think about what that means physically, it means it's really hard to move energy along that fin by conduction, right? All of my temperature drop is going to be due to conduction. Almost none of it's going to be due to convection, right? And that's this line here, where I get this massive temperature drop due to conduction in the x direction, and then basically the fin comes to T infinity for the rest of the way, right? This rest of this line is at T infinity because there's not much of a temperature drop due to convection, right? So those are 2 behaviors that aren't very interesting. More interesting behavior occurs when these 2 resistances are kind of the same, right? Then I get these different lines that sort of are lines where arc conduction and arc convection, arc conduction in the x direction and arc convection are on the same order, right? All right, so let's go back now and think about the kind of model that we can build of this kind of a situation, right? Again, These resistances are super useful for me to understand what's going on, but they're not useful for me to get an exact solution. But what they have let me do is simplify my two-dimensional problem to this one-dimensional problem, right? I'm basically saying that at any y position, whether I'm at the center or the edge, the temperature is the same, right? So I have a situation where the temperature is only a function of x. I should be able to figure out that temperature using a one-dimensional model.